Welcome,
Hi,
my friends.
love to
Hi,
have you.
everyone.
Would you both like to introduce yourselves? Daniela first.
Definitely. Yeah. Hi, everybody. And thanks for tuning in from what seems like around the world and different time zones, which I'm a huge fan of. My name is Daniela Becker. I'm a senior product manager on the Amazon Braket team. I've been with AWS about 3 years, 6 months thereof. We're within Braket. And as part of my role here at Braket, I actually get to work with our quantum hardware providers. So the people that actually produce those fantastic devices that we offer access to on the service. And as such, I'm in a very fortunate position because I get to work with very cool Amazonians like Jordan to build cool products, and with very cool non-Amazonians like Matt to also build very cool things. And I'm super excited for Matt to be here actually to talk about something that we built and launched earlier this week.
Thanks, Danielle. Very flattering. It's also great to be here and see so many people tuned in from everywhere. It's truly incredible. My name is Matt Keeson. I've been at IonQ about 5.5 years. My teams build both all the software that makes our quantum computers work, as well as the platform that makes them available to the world through Amazon Braket.
Thank you both. So, just at a really, really high level, what was the launch this week?
Yeah, I think we talked about it a couple of times now, but Braket is the quantum computing service on AWS. And what that means primarily is we offer access to quantum computers that are out there. And so, long story short, we just added a new one to the selection, and that is IonQ's Aria device. And we're super excited for it to be available on the service, actually, along with its predecessor that's called Harmony, because it is a higher scale, higher quality device. And it also brings an interesting capability called error mitigation to the service for the very first time. And I'm super excited to talk about all of the details of all of those things today.
Sweet. And I know that this is a question we get quite often. Can you tell us why the service is called Amazon Braket?
Oh my God, yes. That along with why are you presenting me with wall brackets on Amazon.com when I search for it online? So I'll answer the second question first, which is it's spelled B-R-A-K-E-T without the C in the middle. And the reason for that is it's actually named after the Braket notation, which is a pretty standard notation in quantum mechanics. Some people also refer to it as a direct notation. And I personally find it a very cool, unique name, but I'm also a little biased when it comes to that.
Definitely.
Awesome. All right. So we've covered what Amazon Braket is, but IonQ. So Matt, tell people who aren't familiar with IonQ, what is it?
Yeah, we are a company. We were founded about 10 years ago by Chris Monroe and Jungsang Kim as a spin out of their combined decades of research at the University of Maryland and Duke University. Our focus is designing and building, the world's most useful quantum computers. Our name basically explains the core of our approach, which, as Jordan said earlier, kind of feels like science fiction. We trap individual ions, charged atoms, in an electromagnetic field in a vacuum to serve as our qubits. And we manipulate them with lasers to perform quantum operations. Ions are actually naturally identical and naturally quantum. And so this approach has proven to be among the most accurate methods for quantum computing to date. And we're super honored to have been available on Braket since the service launched back in 2020.
Yeah, thank you so much for sharing that. So this device that we're launching is Aria. So can you tell us, Matt, about what makes Aria special? I know Daniela mentioned a couple of things, but let's deep dive on that.
Yeah, I mean, it was definitely the most beautiful quantum computer we built to date, but that isn't the most important part. It's actually our most powerful computer available to the public today. So first, it has 25 algorithmic qubits, as we describe it, meaning not only do we have 25 physical qubits, but they're all connected, meaning you can run a gate between any pair of qubits, and the gate fidelities are the highest we've ever offered publicly. So you can run hundreds of entangling operations without hitting the limits of the machine. Hybrid chemistry workloads, variational optimization problems, quantum machine learning. Aria has been put through its paces in a wide variety of domains. And as Daniela mentioned, we've added a new error mitigation capability to help improve your experience further. So we're super stoked to have it available on Braket this week.
Yeah, I'll also jump in to say, I think something that you mentioned earlier, which is really around the quality, something that is super important, obviously, to us, but because it is important to customers. And I think it's worth pointing out, stepping back a little bit, the quantum computers that are available to us today are inherently noisy, meaning, on a high level, take the results that you get from a quantum computer that exists today with kind of a grain of salt. In fact, I think many people like to call the current phase that we're in this kind of noisy intermediate scale con. We're in this era. And so as a result, the fundamental quality that we can offer on those devices, whether it is the qubit quality or, the gate fidelities and so on, is even more important to customers. So we're extra happy when we see our quantum hardware providers, raise the bar with respect to improving the quality of their devices as it comes to kind of next generation devices. And that's certainly the case here for Aria. It's one of the reasons why we're really excited to have Aria on the service now.
This is really cool. I know we've got a lot of people who are new to quantum computing and terminology. So, Daniela, how would you describe what error mitigation is?
Yeah, great question. I know we touched on it a couple of times now, but given that we really can't take the quality of the quantum computers that we have today for granted, one way for us to reduce the effects of systematic noise on today's error-prone quantum devices is error mitigation. And I also am going to call out that error mitigation is different from error correction, which is really kind of aimed at this future world where we have fault tolerance and full scalability and such things that requires a whole different set of science and other things that we don't quite have yet. But maybe people consider error mitigation to be a key tool to kind of get the most out of the devices that we have today. And so more specifically, error mitigation techniques generally kind of take an input circuit, so basically your algorithm, and map it to various implementations of that same circuit and apply some classical pre and post processing to try and improve the quality of the results that you get when you run on a quantum computer today. It's actually an active area of research. There's a variety of methods out there. And we've actually talked to customers that even built their own error mitigation techniques and kind of do research within that. So I think it's super interesting to have built-in error mitigation available on the service now when you use the Aria device on Braket, particularly because customers can flexibly turn it on or turn it off and really see what that does when it comes to their individual use cases and algorithms. And more generally, as for anything on Braket and arguably AWS, you only pay for what you use. It's a pay-as-you-go service, which is really great for customers that are really looking to kind of experiment and understand the technology, all the way up to conducting full-blown research. So error mitigation is available as part of that as well.
Thanks. That was a great explanation. Love that. Well, thank you, Alex. I agree. It is very cool. So Matt, can you actually tell us a little bit about those error mitigation techniques that IonQ has developed, the ones that are going to be, they're now available on Aria?
Yeah, the first error mitigation technique we're releasing publicly is called debiasing. So it turns out there are systematic errors in the computer at any given moment in time. This noise that Daniela was just talking about. The lasers are fluctuating. There's electronic noise affecting some channels, but not others, et cetera. And these bias the computer one way or another way. So to debias, as we call it, we'll run, say, 25 variations of your program, and we'll map your logical qubits, meaning the qubits in your program, to different physical ions. This really actually can help to reduce the impact of noise on your program. And after we've run all these different variations and debiased your circuit, then you can aggregate the runs with a couple different methods, averaging and what we call sharpening.
I think we should see a demo of this. What do you think, Jordan?
I agree, but first we got a question in the chat, which is, what's the deal with the musical names nomenclature?
Yeah. They say there's like only two hard problems in computer science, one of which is naming things. But actually the way our computers work is by shooting ions with laser light that has been modulated into complex waves. Basically, it's a synthesizer. You can't hear it because it's incredibly high frequency, but it actually makes the atoms literally vibrate in response. And that's how we make them do math. A shockingly high percentage of the engineering team plays musical instruments for some reason, including our friends at Braket. So we've always used musical metaphors to explain how different parts of the system work. And we thought it would be evocative for our customers, hence Harmony and now Aria.
Love that.
That is amazing. Wow. And
I think that's really an ongoing theory, isn't it? Every room that you enter, if there's a quantum physicist there, we have to ask if they've also played the trumpet or, any other musical instrument.
A lot of violinists, shockingly. Yeah.
Usually it's like 20 trombonists. I don't know why.
That's so funny. So yeah, let's see this demo. See Aria in action.
Let's do it. I will bring up the AWS Management Console, which if you've never seen it before, I hope you did watch the previous segment, so you should have at least seen it once before. But if not, this is usually where you would land. So in our Management Console, this is kind of your dashboard. Now, of course, I have Braket bookmarked for very obvious reasons, but if you don't, for whatever reason, you can, of course, search for it here. And we'll pull up our Braket service console. And what you'll see at first is basically kind of a dashboard. So it'll give you some kind of shortcuts to different things, and you can actually customize this if you like. Of course, I added Aria as a shortcut here, so you'll see kind of details about the device in a very brief high-level summary up here. Active notebooks, announcements, other kinds of resources, and just recent resources that I wanted to access quickly. And I'll just briefly walk you through kind of the different pieces of the service before we dive into jumping on Aria itself. So if you remember Jeff mentioning it earlier, Braket became generally available in 2020, and we had 3 devices at the time. Now we have 6 of them, which is super cool. And they come in different, what we call modalities or kind of types of devices. So currently on the service, we actually offer 2 superconducting devices. So those are superconducting electric circuits that operate at very cold cryogenic temperatures. One is by Rigetti and one is by Oxford Quantum Circuits, or OQC. We also offer now 2 ion trap devices that we just heard about. So Aria, of course, is kind of the star of the show for today. Harmony has been around since GA of the service, and we're super excited to have both of them here by IonQ. We also have a photonic device by Xanadu, which is the Borealis device. And then last, but certainly not least, we also have a neutral atoms device by Quera that uses Rydberg atoms. And then one more thing I wanted to mention before we actually look at those devices in more detail, you'll see up here that they're classical simulators. And the reason we have them is that we realized customers are looking to run on quantum computers. They really also need tools to kind of build their algorithms and test and iterate on them before they're ready to run on an actual quantum computer. And so for that, we offer an open source Python SDK that customers can use to develop their quantum algorithms, and then a variety of classical simulators that allow you to really kind of test and iterate before you're ready to run on an actual quantum computer, which, by the way, I still think is so cool that we get to do that. Like, you can actually access a real quantum computer out there. I don't think it gets old for any one of us, even though we look at this, on a day-to-day basis. But I'm still amazed at that. I love the sci-fi world that we live in.
Oh yeah, I completely agree. Like, it's always fun when I go to conferences and we have like a little demo up that's like, run an entangling circuit on a quantum computer, and people are always like, wait, really?
Like, yep. I don't definitely hear that too.
Yeah.
So speaking of Aria, I just pulled up the device details card for this particular device. So of course you get a ton of more useful information around, what is Aria, how is it built, and kind of what are different things that it supports, as well as things like its availability windows. So within Braket, we use this notion of availability windows, which basically tells you when is the device actively kind of available for, Braket customer tasks to process, as well as things like its location. So it is located in Maryland, US. I have checked for myself, that is definitely true. And it's also available through our US East 1 region. Now, of course, you can access this device. It's on the cloud anywhere around the world, no matter which AWS region you're in. But basically, this means if you're going to actually run something on the device, your tasks, so basically the circuit representation of what you're going to run, will be in that particular region. We'll see that in a second as well. And then, of course, we have a couple other useful information like number of qubits, very important thing to know, as well as calibration information. So under this tab here, we have this really cool picture.
I'm sorry, I haven't seen this topology image before. This is so cool.
Yeah,
Isn't it the best thing? I'm really excited about this.
I like another tattoo of that. That's so cool.
It is really, really neat. So what you see here is basically all these different 25 qubits, and IonQ offers all-to-all connectivity on their devices. And that's why you see these like fun little lines in between. So it's a really neat picture once you actually start looking at it. Mesmerizing, really.
So for the novice, it's not artwork.
Oh yes, true. Matt just sent me this picture probably a week ago, so that is how it got here. But yeah, that is a topology graph, and then you of course also have additional information about like the fidelities of the device, which basically think of it as like the snapshot of kind of the current status of the device and how it's calibrated. All of which very useful information that kind of our customers need on a day-to-day basis as they interact with those devices. Last thing I want to point out on this page is this thing called the device ARN, or I guess we say ARN, which stands for Amazon Resource Name. So something that's super neat about using Braket to access all these different devices is if you want to change your workflow and just target a different device, for the most part, all you need to do is just change one line of code and change which device you're actually targeting. So in this case, you would be using this exact ARN as kind of the ID of the device that you're targeting. And we'll see that one in a second here as well. Before I actually get to the specific example, I do just want to point out there are various ways for you to interact with Braket. So as I mentioned earlier, we have an open source, Python SDK. You can download that and use that in your local development environment. You can also use managed notebooks, which is what we'll be using here. So I'll just pull up one that, of course, I prepared in advance. This just has the advantage that, you don't have to manage any of the infrastructure on this, and you can kind of just use that here and just pull it up when you need it. And in here, what I prepared was obviously kind of a demo notebook, which is kind of a toy example to show basically three things. One, how do you run a task on the Aria device? Two, how do you enable debiasing? As I mentioned earlier on Braket, you can choose whether you want to turn it on or off. And then three, how do you look at sharpened results as well? And we'll actually have a little plot in the end here. I'll point out this is a toy example, so it is a little bit smaller kind of in nature, but we do have some really cool examples in our lunch blog, which I'm sure somebody is about to drop the link to, as well as our example notebooks. And all of this you can find in our example notebooks. If you want to follow along or do this by yourself, please have at it. It's really cool and super fun. So for any basically Braket workflow that you would do, it kind of consists of 3 steps. I realize I really have a preference for things in 3, so you'll hear a lot of 1, 2, 3 today. So first off, you want to select the device that you're going to target. So we're actually going to use exactly that device ARN that I pointed out earlier to target our Aria device. And then 2, you want to define the actual circuit that you're going to run. Think of the circuit as just kind of the algorithm that you want to run on your device. And we're going to run a quantum phase estimation algorithm. And I'm not going to go into the detail of how that's defined. But one thing that's kind of fun to point out is it is a pretty important algorithm that shows up as kind of a subroutine in many other algorithms that are out there. If you've heard of Shor's algorithm, which is a pretty commonly known one that people love or hate depending on how you look at it. Phase estimation is absolutely critical for that one. So you definitely need some form of phase estimation if you wanted to implement some form of Shor's algorithm as well. So that's what we're going to use here. It has 5 qubits, and we'll see those results in a second. So I'm just going to hit execute on this one. And now here is where sort of the interesting magic happens. So that's the execution piece. Within Braket, we have this notion of tasks. So a task basically represents a circuit that you're going to run on a device. And then for each task, you associate a certain number of shots, which basically means the number of times you're going to execute that circuit on the device. So in this case, what you can see in this one line of code is I'm basically saying I want to execute the circuit that we just defined, and I want to execute 2,500 times on the Aria device. So we're going to hit run on that, and it's going to output a task ID over here, which is this task ARN. Now, if we wanted to actually go back into the console and see, you'll see that this exact task is now queued in my console here. So something that's neat in the Service Management Console is that you can monitor all of your resources as they're here. And of course, we're an AWS service, so obviously we're fully integrated with all of the different tools and other services that you might already be familiar with to monitor your workloads, review your results, analyze things. So all of that is of course fully integrated. In here, you'll get more information about what is the task that you just kicked off, when was it created, which device was it targeted at, and all those kind of useful pieces of information. And down here, whenever you actually have results, is where you'll reference your results location. As you may or may not have noticed, I actually didn't specify where I wanted my results stored, which we use Amazon S3, so our storage service for. So in this case, Braket just picks a default one. It'll be linked. You can always find it later on, so you don't have to worry about it. But if you want it in a specific place, that would be where you would specify that. So in this particular case, we're actually not going to wait for that task to complete executing. I'm going to pull something that I executed previously, just so I don't bore anybody here. So that's what's happening here. So basically pulling from a task that I executed beforehand. And what happens here is we're going to grab our results and the measurement probabilities that you're going to see. And I'm going to output those on the screen as well. So you see fun stuff like this, all these different bit strings and numbers and probabilities associated with each one of them. And the fun part is that is basically what happens when you execute a task by default without debiasing. It's just going to grab the results based on what we hear back from the device. But in order to turn on debiasing, all you need to do is you add a device parameter that's basically called error mitigation and debias over here. So pretty straightforward. Same thing, we're going to execute that task. And I'm going to kick that off as well. Same story here. I'm not going to make you wait for that to come back. I'm going to pull something that I generated beforehand. But basically what we're going to do is we're going to grab those results and the measurement probabilities just like before so we can compare them. And same thing here. So now that we've done our debiasing, since sharpening is really a classical post-processing step, on Braket, you actually always have access to also the sharpen probabilities. And all you need to do is kind of grab that from the metadata of your result. So I'm just going to execute that. By the way, I'm stepping through these as separate blocks. Obviously, you don't have to do that when you define your code. This is just for the sake of the demo. And lastly, now that we have all of our different results, we can plot them and compare, and we'll see hopefully some fun colors. So what you see here is basically the comparison between what happens when we don't apply any error mitigation, so that's the blue bars. We apply debiasing, which is the orange one, and then we apply sharpening, which is the green one. And those percentages here that you see are the different fidelities. So you can clearly see that you get some benefit from turning debiasing on. You get a lot of benefit from turning sharpening on. And the reason for that is sharpening is really good at kind of pulling out contrasts. So basically, if you have sparse output distributions, which is definitely the case for something like quantum phase estimation, it's very good at pulling out the one that seems to be the highest probability bit string, which in this case is actually the correct result, and therefore you get this 100% fidelity. So overall, that is what you need to do to use debiasing and sharpening on Amazon Braket and to access Aria.
Thanks so much for that. That's great, Daniela. Very cool. Yeah, I have no notes.
Perfect.
Jillian?
Yeah, so I guess, Daniela, do you have any advice for people on how they can actually get started?
Yeah, absolutely. There's actually a couple of things I want to point out, which we only touched on using tasks, like standalone tasks on Braket, but we actually have a concept called hybrid jobs on Braket as well. And the reason we do is because we recognize that, in this current, I'll call it NISC era again, it is very likely that customers will want to run, hybrid variational algorithms, where basically, you have QPUs and classical compute kind of working as co-processors. And so that customers don't have to worry about kind of standing up the classical infrastructure and managing that interplay. That is where, we do that. That is literally what AWS does on a day-to-day basis. So if you use hybrid jobs, we take care of spinning up the classical resources that go along with your hybrid algorithm. And it has the advantage that any of the tasks, quantum tasks that get spun out of your job, get priority access to the device. So you can make sure that those tasks always run kind of back to back on the device. And that is super neat, especially for, workflows that customers want to run on Aria. So checking out hybrid jobs, great place to start and wanting to kind of ramp up on Aria for sure. And then the other thing I'd love to point out as well is we, of course, have a lot of research customers, especially from the academic sphere. So if you are an academic researcher or belong to an academic institution or are interested in doing research on QPUs, we actually offer a credits program for research customers, which also offers credits for you to apply to Braket when you want to run on it, which great place to start for sure.
That's cool. Matt, and then from your perspective, any just like piece of advice or place where you can suggest people can kind of go? You want to learn more?
I mean, I think, yeah, two things. I mean, first of all, like just democratizing access to quantum computers is essential to unleash their full potential, which is a huge part of why we're on Braket. If you think about when the first digital computers came out, 80 years ago, people couldn't possibly imagine we'd all have smartphones and be streaming globally right on AWS on air. Everyone listening right now is part of this first generation with access to real quantum hardware. which means there's applications that no one has contemplated yet that you will build to change the world, which, you know, I'm super excited to see. I think the Braket team has put together a huge amount of great learning resources to get started. And I think the most important thing is just to play. You know, don't be afraid to actually go in, open up your notebook on Braket and cause lasers to shoot at atoms, you know, somewhere in Maryland. We'd love to see that.
I love it. Yeah. And then I'll also call out some resources that Eric from the Amazon Braket team pointed to. So Eric pointed out the launch blog. So you can go here to check out the launch blog to learn more of it in detail about what is it we've been talking about. And another link here in this long message that Eric was also responding to Alex. But you'll see here, if you go into GitHub, Amazon Braket examples, there's more examples that you can go to learn more, which I want to, because this is just so fascinating, this topic. Matt, Daniela, thank you so much for being here today.
Thanks for having us.
Thanks for having us.
Wow.
What a great show.
This was amazing. I mean, I'm just like so inspired. There's so much that I want to learn about. Like, I mean, I was joking, you know, earlier about like we could start a startup of being able to have quantum computing and and life sciences, doing drug discovery, being able to detect Jeff Barr earlier, using AI. It's just an amazing time to be in, and the access that people have to all these technologies.
Yeah, I mean, like the wild thing is that it's all literally accessible to anyone. Like you can just sign up for an AWS account, you know, go ahead. Yeah, exactly, Alex. Like
bright minds like you, Alex, like you, Suraj. I mean, all of you here, can learn more and actually like get started. I think that's what's so cool about all this stuff. And I'll share one more link that Eric shared before we sign off for today. Is a great place to ask questions. If you want to learn more about quantum computing, it seems like there's a lot of people who are new and are just kind of curious to learn more about that space as well. So that's a great call out, Eric. Perfect. Well, thanks everyone for being here today. I know we had some people, Alex, this was your evening. We had people Ivory Coast,
New Delhi,
France,
Italy.
I mean, all over the world who are coming to watch with us. So let's see, we've had Mark. So thank you, Mark, for joining us today. Jeanette, thank you. Alex, all of your questions for being us. Alex, Masha, thanks so much for being here with us today. Suraj, thank you so much. Fernando, thank you so much for being here today. We do this again every single Friday. So it's always at the same time. So where we just bring different people from AWS to talk about the news and also exciting feature launches. So join us next Friday for the next one. All right. Thanks everyone.